In the first part of Chapter 3, Section 2, we will learn about the basic concept of variation. And in the second part, we will be introduced to the concept of the standard deviation. We will learn the formulas used to compute these statistics. However, at this time, memorizing the formula is not as important as understanding and interpreting the meaning. Variation is the single most important topic in statistics. So this is the single most important section in this book. This section presents three important measures of variation, including the range, the standard deviation, and the variance. These statistics are numbers, but our focus is not just on computing those numbers, but developing the ability to interpret and understand them. The range is the difference between the lowest and the highest values in your data set. The standard deviation is a measure of disbursement in statistics. Disbursement tells you how much of your data is spread out. Specifically, it shows you how much of your data are spread out around the mean. And finally, variance measures how far a data set is spread out. It is mathematically defined as the average of the squared differences from the mean. Note, when we're rounding the value of a measure of variation, we want to carry one more decimal place than is present in the original data set. The range of a set of data values is simply the difference between the maximum data value and the minimum data value. So we would say that range equals to the maximum data value minus the minimum data value. In this data set of 4, 6, 9, 3, and 7, the minimum data value is 3 and the maximum data value is 9. So the range of this data set is 9 minus 3 equals to 6. The range uses only the maximum and the minimum data values, so it is very sensitive to extreme values. So we would say the range is not resistant. Recall that a statistic is resistant if the presence of extreme values or outliers do not cause it to change very much. Because the range uses only the maximum and minimum values, it does not take every value into account, and therefore it does not truly reflect the variation among all of our data values. Let's go back to our Verizon data speed example and find the range of that data set. Recall that our data set is 38.5, 55.6, 22.4, 14.1, and 23.1. The highest or maximum value of our data set is 55.6, and our minimum value is 14.1. So we would say that the range of this data set is 55.6 minus 14.1 is equal to 41.5 megabits per second. The standard deviation of a set of data values, denoted by lowercase s, is a measure of how much the data values deviate away from the mean. The notation used to represent the standard deviation are as follows. The sample standard deviation is denoted by a lowercase s, and the population standard deviation is indicated by the lowercase sigma. Here we have two formulas for the standard deviation of a sample. The first formula is the original standard deviation for a sample, and the second formula is a shortcut formula. In the first equation, you can see that the standard deviation takes into account how far each observation in your data set is from the sample mean of your data set. And later, we will use a table to demonstrate how to calculate the standard deviation of a sample. Let's review some important properties of the standard deviation. The standard deviation is a measure of how much, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, the value of the standard deviation will never be negative. It is 0 only when all of the data values in your data set are exactly the same. And finally, the larger values of the standard deviation indicate a greater amount of variation among your data values. Some more properties of the standard deviation include the following. The standard deviation can increase dramatically with one or more outliers. The units of the standard deviation, such as minutes, feet, pounds, are the same as the units of the original data values. And finally, the sample standard deviation is a biased estimator of the population standard deviation sigma, which means that the values of the sample standard deviation do not center around the value of sigma. So let's use our data set of Verizon data speed times, and we'll calculate the sample standard deviation for that data set. The first thing we'll want to do is calculate the sample mean of our data set. And remember, the sample mean is calculated by summing up all of our observations and dividing by the number of observations. So our sample mean with this data set is equal to 30.74. The next step is to take each observation in our data set and subtract from it our sample mean. And we've done that in column 2. You can see that our first observation, 38.5, I subtracted 30.74, and that gave us a value of 7.76. We do that for each observation in our sample data set. You can see that some of those values will be positive and some of those values will be negative. So we handle that by squaring all of those values. So that'll be our third step. You can see in our third column, we've taken the square value of each of those values in our second column. We sum up all of the values in our third column, and that gives us our numerator for our standard deviation equation. So now you can see that our standard deviation for this sample is going to be the square root of 1083.05 divided by n minus 1. In this case, we have 5 observations, so we're going to divide it by n minus 1, or 4. So then our next step is to take the square root of that, and finally we see that our standard deviation for our data set is 16.45 megabits per second. This slide demonstrates how we would calculate the standard deviation using our shortcut formula. I won't go through each step like I did on the previous slide, but you can see that I've added an additional column to our table, and that column is the square of each observation in our data set. So you could take this information and plug it into your formula, and you would end up calculating the same standard deviation as we did with the original equation. The range rule of thumb is a crude but simple tool for understanding and interpreting standard deviation. It is based on the principle that for many data sets, the vast majority of the sample values will lie within 2 standard deviations of the mean. We could improve the accuracy of this rule by taking into account such factors as the size of the sample and the distribution, but for now we'll just sacrifice accuracy for the sake of simplicity. The concept of significance as shown here will be presented in greater detail in later chapters, specifically when we learn about the topic of hypothesis tests. Hypothesis tests are also known as tests of significance. The following rule of thumb is based on the population mean mu and the population standard deviation sigma. This rule applies to large samples that represent the population. Since the sample is large and representative of the population, we could replace our population mean and our population standard deviation with our sample mean and our sample standard deviation respectively. So we would say that significantly low values are the mean minus 2 standard deviations or lower, and significantly high values in our data sets are the mean plus 2 standard deviations or higher. And finally, we'd say that values are not significant if they are between the mean minus 2 standard deviations and the mean plus 2 standard deviations. We can use the range rule of thumb for estimating a value of the standard deviation S. In order to roughly estimate the standard deviation from a collection of known sample data, we could use the equation S is approximately equal to the range divided by 4. Now let's look at the formula for the population standard deviation. As you can see, the only difference between the sample standard deviation and the population standard deviation is the value in the numerator. For the population standard deviation, we will divide by the population size, capital N. A word of caution, often when using a calculator or software with statistical functions already programmed in, you want to make sure to identify the notation that is used by the calculator or software so that you know if you're calculating the sample standard deviation or the population standard deviation. So far, we have used the term variation as a general description of the amount that the values of the dataset vary among themselves. Sometimes this variation is referred to as dispersion or spread. But now let's examine the term variance. The variance of a dataset is a measure of the variation equal to the square of the standard deviation. So the sample variance is simply the square of the sample standard deviation. And the population variance is simply the square of the population standard deviation. So let's review some notation. S is the notation we use for the sample standard deviation, and S square is the notation we use for the sample variance. Sigma is the notation we use for the population standard deviation, and sigma square is equal to the population variance. Let's review some important properties of variance. The units of the variance are the square of the units of the original data values. The variance is not resistant and can increase dramatically with the inclusion of outliers. The value of the variance will never be negative. It is 0 only when all of the data values are the same number. And the sample variance S square is an unbiased estimator of the population variance sigma square. We say that a statistic is unbiased if that statistic is neither an underestimator or overestimator of a population parameter. So when we're calculating the sample standard deviation, why do we divide by n minus 1? The reason is that dividing by n minus 1 corrects for the bias of using a sample mean instead of the population mean. There are only n minus 1 values that can be arranged without constraint. That is to say, if you know the sample mean and all but one of the values, you could calculate what that last value would be. Statisticians say that there are n minus 1 degrees of freedom. When we divide by n minus 1, the sample variance tends to center around the value of the population variance. However, if we divide by n, the sample variance tends to underestimate the value of the population variance. The empirical rule states that for a normal distribution, nearly all of the data will fall within 3 standard deviations of the mean. The empirical rule can be broken down into 3 parts. The first part states that about 68% of the values will fall within 1 standard deviation of the mean. The second part states that about 95% of the values will fall within 2 standard deviations of the mean. And the third part states that about 99.7% of the values will fall within 3 standard deviations of the mean. When applying the empirical rule to a data set, the following conditions are true. Approximately 68% of the data will fall within 1 standard deviation of the mean. In mathematical notation, this would be represented as the mean plus or minus 1 times the standard deviation. Also, approximately 95% of the data will fall within 2 standard deviations of the mean. The mathematical notation for this is the mean plus or minus 2 times the standard deviation. And finally, approximately 99.7% of the data will fall within 3 standard deviations of the mean. The mathematical notation for this is the mean plus or minus 3 times the standard deviation. Let's consider an example using IQ scores. IQ scores have a bell-shaped or normal distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ scores are between 70 and 30? Because IQ scores are normally distributed with a mean of 100 and a standard deviation of 15, we can use the empirical rule to find the percentage of IQs that are between 70 and 100. If we recall the empirical rule, as we described before, about 68% of the individuals will have IQs that are between the interval of 100 plus or minus 1 times 15. That gives us a range of 85 to 115. So we would say about 68% of individuals have an IQ between 85 and 115. About 95% of individuals will have an IQ score in the interval of 100 plus or minus 2 times 15. And so that interval will be 70 to 130. So we can say about 95% of individuals will have an IQ score between 70 and 130. And finally, about 99.7% of individuals will have an IQ score of 100 plus or minus 3 times 15, or an interval of 55 to 145. So, using the empirical rule, we can say that about 95% of individuals will have an IQ score that is between 70 and 130. Chebyshev's theorem is used to find the proportion of observations you would expect to find within k observations from the mean. For a population or sample, the proportion of observations is no less than 1 minus 1 over k squared, where k is any positive number greater than 1. Let's set k equal to 2. So we want to find the proportion of the data sets that will fall within 2 standard deviations from the mean. So our formula is simply 1 minus 1 over 2 squared, and that equals to 3/4 or 75%. So we would say that at least 75% of all values lie within 2 standard deviations of the mean. Now let's set k equal to 3. For k equal to 3, then we have 1 minus 1 over 3 squared, which is equal to 8 over 9, or 89%. And we'd say that at least 89% of our values lie within 3 standard deviations of the mean. Let's go back to our example of IQ scores. Recall that IQ scores have a mean of 100 and a standard deviation of 15. What can we conclude from Chebyshev's theorem? By applying Chebyshev's theorem, we can reach the following conclusion: that at least 75% of IQ scores are within 2 standard deviations of the mean, or 75% of IQ scores are between 70 and 130. Also, we could say that 89% of all IQ scores are within 3 standard deviations of the mean. That is to say, they're between 55 and 145. It's important to note that while the empirical rule applies to bell-shaped or normal distributions, Chebyshev's theorem will apply to any data set. However, Chebyshev's theorems are only approximates and have limited usefulness. It's a good practice to compare 2 sample standard deviations only when the sample means are approximately the same. When comparing variation in samples or populations with different means, it's better to use the coefficient of variation. We would also use the coefficient of variation to compare the variation from 2 samples or populations with different units of measurement, such as comparing the variation of the heights of men to the weight of men. The formulas for the coefficient of variation are, for a sample, CV equals to the standard deviation divided by the sample mean times 100%. And the population coefficient variation is the population standard deviation divided by the population mean multiplied by 100%. Recall in a previous slide we learned that a statistic is unbiased if that statistic is neither an underestimate or overestimate of the population parameter. The sample standard deviation is a biased estimator of the population standard deviation, which means that the values of the sample standard deviation do not tend to center around the value of the population standard deviation. The sample variance is an unbiased estimator of the population variance, which means that the values of the sample's variance tend to center around the values of the population variance, instead of systematically tending to overestimate or underestimate. This is the end of Chapter 3, Section 2. Please proceed to Chapter 3, Section 3.